Okay, everybody. So this video will be a continuation of some videos I've made already about integration. But there's another technique that I need to introduce called u-substitution. So as you see here, I just titled the first slide, Integration by Substitution. And just as a matter of fact for this topic, I'm going to have to review a little bit and talk about some terminology, some vocabulary, definitions, whatever you want to call it. And you might not be interested in that. I think some people, for right or wrong, if you have kind of an immediate gratification mindset, maybe you just want to see the problems worked, okay? And so you can, this is a video. You can skip around to wherever you want to. All right, okay, so no big deal. If you want to just skip to the problems, skip to the problems. You're free to do that, but it wouldn't be right if I just did problems and I didn't explain the concepts and I didn't tell you the terminology and so on. So I will do that. I will take part of this video to just tell you about terminology, okay? And I'm afraid it's going to be a long video, but like I said, if you don't have the attention span for it, you can skip around, you can watch it in parts, or do whatever you want. Okay. So first of all, here's a completed statement. This problem is complete right here. It says the indefinite integral of sine x is negative cosine x plus c. Okay? We call this an indefinite integral. And we call this the antiderivative of sine x. This capital C right here is a constant. It's an arbitrary constant that we call the constant of integration. Okay? All right. So why is this the answer to this? Well, we call this the antiderivative. So you could check any of these statements by saying, well, look, the indefinite integral of sine x is negative cosine x plus c, because if I take the derivative with respect to x of negative cosine x plus a constant. Now, I don't know what that constant is. It's not specified. It can be anything. It doesn't matter. If I take the derivative of negative cosine x plus any constant, it will be sine x, right? Because what's the derivative of negative cosine? It's sine. Plus, what's the derivative of this constant? So I don't know what that constant is. Doesn't matter. The derivative of a constant, 0. Okay, so it checks out. This is the answer to that, because if I take the derivative of this, I get that, all right? That's how these work. All right, a little bit more about this constant here, which we call the constant of integration. There could be lots of answers to this question, right? I said that constant can be anything, and it's going to check out. What makes this statement correct is if I take the derivative of this, I get that, okay? But why is there constant integration? Well, just maybe to be dramatic about it, if I took the derivative with respect to x of negative cosine x plus 4, it would be sine x. If I took the derivative with respect to x of negative cosine x minus pi squared, well, pi squared, that's a constant, and I'll get sine x. So yes, the derivative with respect to x of negative cosine x plus any constant is going to be sine x. So that's why there's a constant of integration on this, okay? All right, so let's do this one. So what is the indefinite integral of secant squared x dx? I don't know. Do you see how it works? This would be a correct statement, because if I take the derivative of the thing on the right, I'll get this function right there on the left, sine x, okay? All right. So let's see, do you know anything that would do that? Do you know anything that if I took the derivative of it, I would get secant squared? And that would be tangent. Just as a matter of fact, the derivative of tangent is secant squared, okay? So I could say, well, there's your answer. Okay, there's your answer. The derivative of tangent secant squared. But that would be a little bit incomplete, because it's not the only answer, right? You see what I'm getting at up here? The derivative of tangent x plus any constant is going to be secant squared of x. So there's my answer. The indefinite integral of secant squared x dx is tangent of x plus c c being the constant of integration, being a constant. All right. Okay, now why is this my answer? Well, the justification for all these problems is the same. The reason why this is the answer is because if I take the derivative with respect to x of tangent of x plus some unspecified constant c, then I will get secant squared of x. That's really the only justification that there is for this being correct. All right? Okay, so there's some introductory information about this. Now, I wish I could just make this extremely simple and just tell you everything in 30 seconds, but I'm afraid it's not like that, so there's more to talk about. What is the dx? Here's the problem I just did. I haven't really given any attention to the dx. This is the integral symbol, that's what that's called. Secant squared is the function. If I take the derivative of tangent of x plus c, I get secant squared. What about the dx then? Well, the dx is not involved in working the problem, okay? Well, you might say, why is it there then? Well, because later on with some more complicated problems, we need to think about the dx a little bit. But for now, like, we don't have to worry about it, okay? But it should match the variable that you're using. All right, so secant squared x, that's a function that involves x, and the dx, it has the variable x in it. Dx is also called a differential. Notice that I didn't write dy when the variable here is x or something else, okay? So this, generally problems will look like this. There's our integral symbol. This is the indefinite integral of this function. That function is called the integrand, and so on. And then dx, that's the differential, and it will match the variable that this function has. Okay, so that's how these things are put together. Let's look at a few examples where I think really, like, I can talk about this in theoretical terms all day, but until people see examples, it's not really going to sink in. So what about this one? What's the indefinite integral of 2t? Is there something you could take the derivative of and you get 2t? Notice I put 2t dt. That differential right there needs to match the variable in this function. That's a function, 2t. All right, well, that would be t squared. Is the derivative of t squared 2t? It is. So 2t plus c. All right. Now, I just thought of that one. I mean, there is a method for getting that answer, but like for right now, can we agree that the derivative of t squared plus some constant is going to be 2t? That's what makes that correct. Okay. I want to emphasize this, that is correct, because if I took the derivative with respect to t being the variable of t squared plus c, then I will get 2t. Because the derivative of t squared is 2t plus the derivative of that constant 0. All right, I hope that's sinking in. I'm completely aware I'm repeating myself about that, but I want to make sure that it really sinks in for you. What about this one? Antiderivative of pi dr. What could we say? Pi is a constant, pi x. Would that be the answer? Pi x plus c. Would that be right? Is the derivative of pi times x pi? I guess. I mean, yeah, pi is a constant, but that dr right there is signifying that the variable that we're working with is r. Now, that being pi is just a constant, you'd have no way to know. Like this 2t, t is the variable, dt is the differential. Here, pi, well, pi is a constant. If that's all you had, you wouldn't know what the variable was, okay? But dr says, all right, the variable that we have is r. So here we go. Here's my antiderivative. It's pi r plus c. What's the derivative of pi times r plus c? Pi is a constant. Oh, you know what I'm about to say. All right. Here's my answer. The reason why this is correct, in case you haven't noticed so far, is because if I take the derivative with respect to r of pi times r plus a constant, then that is in fact pi. All right? That's why that's the answer. We'll do one more. Cosecant squared. Cosecant squared u du. All right, do we recognize that one? I'm seeing that kind of like this. The derivative of tangent is secant squared. The derivative of tangent plus a constant, still secant squared. There's something like that. Do you remember it? You might even have to look it up, but we've seen something somewhere before that had a derivative like similar to cosecant squared. It was cotangent, okay? My answer here is negative cotangent of x. Well, in the case where my variable is u, negative cotangent of u plus c, okay? All right, there's that one. Why though? Well, I remember, or I look it up, or maybe I have a formula sheet, and I am aware that the derivative with respect to u of negative cotangent of u plus c is positive cosecant squared u. The derivative of cotangent is negative cosecant squared. So the derivative of negative cotangent is positive cosecant squared. So that's why I put it as negative. But it's like the same rationale as the others, okay? So all right, yeah, we can have different variables. This part is called the differential. And we don't, at this point, we don't really use this to work the problem, but it does indicate the variable that we're using, all right? Okay, but nonetheless, every answer is checked or verified the same way, all right? Okay, so next thing, just the way it is, there are lots of rules. There just are, and there's no avoiding it, all right? I don't want to talk like at length about all the rules. I think what I'd like to do is have this slide here, and you can see all the rules. And oh, I can't even list all. I mean, there's too many. There's way too many. But I've got the major ones right here. And if we ever needed anything else, then we'll have a way to figure it out. Okay. So what's the antiderivative of a constant with respect to x? That constant times x plus c. Why is that? Is there any? Do these rules have any rationale to them? Well, yeah. If you took the derivative of this, you'd get that. That's why. What about this one? Okay. X to the n power. N is any constant except negative 1. Well, there's your antiderivative. There's your indefinite integral. Why? Well, if you take the derivative of this, you get that. All right. This one, same thing. Plus and minus. Can you split up an indefinite integral across plus or minus? Yeah, that's what that says. You can work these one at a time and add or subtract the answers as given. All right. And let's see. Oh, okay. What if you have a constant times a function? Okay, k is a constant. Well, you can remove that constant from your indefinite integral and just work that one. Okay, so it's like you can pull this constant out, work that. When you're done, multiply them together. And these, all right, well, they all have the same rationale. If I take the derivative of this, I'll get that. All right, now, so there's lots of rules. I won't say anything else about it, but I'm going to keep this sheet handy in case I'm doing a problem and I want to look back at it and tell you, hey, here's the rule that we need. All right, so I'll put this right next to me so that I have it when I need it. Okay, so we need to learn a new technique. And I have already posted a video about how to work a problem like this. But I haven't told you how to work something like this. Okay? So first, let's do this one just to get our mind thinking in the right direction. And then we'll learn something a little bit different. All right? Okay, so first of all, how can you solve this problem? Is there a technique to it? It's not quite like this one. I mean, at least me, I just don't know the answer. Like this one, I just know the answer. I know that if you take the derivative of tangent, you get secant squared. Because I've learned that before. All right? That's why I know. But, you know, this one, it's not like I have that memorized. I don't know what it is. So there's a technique to it, and the technique comes down to knowing some of the rules, okay? So here's what we do. First, I can split these up like this. I showed you a rule where you can split up the integral across a plus or a minus. So I'll do this one. I'll work out 4 over root x. and then I'll subtract, and then I'll do this one. Okay? I'll work them individually. What else? What about the 4 and the 9? Because I've got a rule for x to the negative 1/2, and I've got a rule for x to the 9th power. So see this rule right here? It says antiderivative, or the indefinite integral of x to the n power is x to the n plus 1 power over n plus 1 plus c. N is a constant, except it can't be negative 1. All right? So, well, that's what I want. That'll do this one and this one. What about the 4 and the 7? What do we do with those? Well, then that would come down to this rule. You got a constant times some function. Just remove the constant, work this one however you need to, and then multiply them together. So it's like I can do this. And of course, when you learn how to do this, or if you understand it, you don't have to write a bunch of steps every time. Some of this will go on inside your head, and that's fine. But for the record, I'm telling you, I can take out the 4, I can take out the 7, I can split it up across the minus. All right? The rules allow us to do that. Now, what's your answer to this one? Well, 4, okay. X, so I add 1 to this, so I take negative 1/2 plus 1 over negative 1/2 plus 1. Okay, that's what that rule said. I carry down the minus and the 7, and then I add 1 there, and there, okay. And then there's always a constant of integration that I have to throw in there. All right, so I got that. What's this turn out to be? 4x, okay, what's that number? 1/2, and that's 1/2 down here, minus 7x, and that's a 10, and a 10 plus c. My final answer, doing a little bit of simplifying. 8, because 4 divided by half is 8, root x, because that's x to the 1/2 power, minus 7/10 x to the 10th power plus c. All right, that's how you do that problem. Okay? It completely comes down to being aware of this rule, and this rule, and of course doing the math right, okay? But it's just rules. You have to learn the rules, and that might take some practice. Now, okay, so we did that one. How can we do this one? Now, I need to get you to notice that this is more complicated than the rules allow. Okay? Can you split up across a multiplication? There's no rule for that. You cannot split an integral up across multiplication. So, for example, say you had a problem that was one function times another function. That is definitely, absolutely not equal to the antiderivative of the first function times the antiderivative of the second function. Definitely not. Don't do that. Okay? You cannot split up this integral across multiplication. Addition, subtraction, okay, but not multiplication. Can't do that. All right? I mean, these are all antiderivatives, so you'd think whatever rule would apply for derivatives would also similarly apply for antiderivatives, and that's true. So you can't take the derivative of a product just like that. There's a special rule for it called the product rule. So antiderivatives work the same way. You can't apply the antiderivative to a product like this. Turns out there's a special rule for this that we don't learn in Calculus 1. But you can't do it that way. I can't split this one up. Okay? All right. And I can't use this rule by itself because it's just not that simple. I can't split it up. I can't use this rule. I can't use, none of the rules really apply to this the way it is. So here's what we do. Okay? We make a substitution. We change the variable. And I can't tell you, at least now, what the rationale is for this. We'll have to get used to this. But we'll take this problem and we'll substitute. You know what the word substitute means? I mean, in place of 1 plus x squared, we'll put u. And in place of 2x dx, we'll put du. All right? This will change the variable of the integrand to u instead of x, and it will transform it so that we can work it. This substitution will turn this into a problem that we can do. All right? Now, a little bit more about this. This is initially chosen just as a substitution. This is a consequence of that. When we choose our substitution, we get this part by taking the derivative of each side. So the derivative of u is 1, but that's a u derivative, so we put 1 du. The derivative of 1 plus x squared is 2x, but that's an x derivative, so we say 2x dx. Now that's just the method. That might take a little bit of getting used to. Right? And if you want to skip straight to the problems and just work go do that. But here I'm telling you what the rationale is. Okay? So all right, there we go. Now, so let's make this substitution then and see what happens. Now first, just to make this as bold as possible, like hopefully making it as obvious as possible, I'll do a little bit of rearranging. Can I rearrange like this? Yeah. I mean, these are all just multiplied together, so it doesn't matter the order you multiply things. It's, the way we understand this is it's all multiply. 1 plus x squared to the 9th power times 2x times dx. Okay? All right, so I can rearrange it as I see fit because it's just multiplication. Now, suppose I make the substitution here in this step. What's it going to look like? Well, in place of 1 plus x squared, we're going to put u. And in place of 2x dx, we can put du. That is a much easier problem than this. This substitution turned this problem into one that is as simple as it gets. All right? When we see this, now it's easy. What's the antiderivative of u to the 9th power du? Well, that would be this rule right here. But instead of the variable x, we got u. That's okay. And the power is 9. All right. So that'd be u to the 10th power over 10 plus c. The substitution simplifies this problem to a point where it's as easy as it could be. Final answer. Okay. If my original question had a function in the variable x, my answer should also be in the variable x. I'll resubstitute to put this answer back in terms of x. U is the same thing as 1 plus x squared. So this is going to be 1 plus x squared to the 10th power over 10 plus c. All right. So there's our answer. Now, I don't really have, I told you this video would be complicated, and if all you want to do is work problems, then just fast forward to the point where I'm working the problems. I told you that, you're free to do it. But I think that you should learn the conceptual basis and the details, even though that might be a little harder on the front end. And one thing I want to do to emphasize this, that answer's right, is I'll check it, all right? If you check these, I think you'll understand better the method of substitution, okay? So I'm going to go ahead and check this. If that answer is correct, then if I take the derivative with respect to x of 1 plus x squared to the 10th power over 10 plus c, if that is right, when I do this, I should get this. That's how they all work. It doesn't matter how you got the answer. They're supposed to work that way. Okay? So for this, I've got a constant of 1 over 10, then times the derivative of 1 plus x squared to the 10th power. And with the chain rule, it looks like that. Plus the derivative of that constant. Well, that is a constant, so its derivative is 0, so I get this. All right, and then what happens? Well, I got 1 over 10 times 10, so that's 1. That cancels. And that will leave me with 1 plus x squared to the 9th power 2x. Okay, and that does check out. That's what I started with right there. Okay. Now, when we make these substitutions then, it's really just like the chain rule in reverse. When I check it here, it's by the chain rule. This answer kind of unfolds into that if you check it. The 10 goes to the front, cancels the 10. makes that a 9. But then when you take the derivative of the inside, you get the 2x. It's really just the chain rule unfolding. Okay? All right. Now, at this point, let's practice this. Okay? So I know I'm explaining a lot of the theoretical stuff about this and the terminology, and I'm checking my answers, and I'm doing a lot of things, and it may be getting lost with it. So let's just, I mean, that's math though, I'm sorry. Let's focus on this. At some point we gotta focus, all right? So let's focus on just using the substitutions. Let's take a problem, take some substitution, turn it into one that's easy, and work it, all right? Let's just focus on that for now. All right, so like here's a selection of 3 problems where I tell you what I want you to substitute, and I want to see if you can get them. So if you want, you can look at these, pause the video, see if you can get them right, and then watch me work them, verify your answers. Okay? So say in this problem right here, now that's kind of a complicated problem, and I have no rule for this problem. Like it's not here. It's not as simple as any of these rules indicate. Okay? So we're going to make this substitution with the aim of reducing it and simplifying it. Now, if you choose, and I know you didn't choose this because here I'm telling you that's the substitution, but if you choose this or if this is the substitution, that's what you put in for the x. Okay? The dx is another story. So if this is our substitution, we'll take the derivative of each side of this, and the other end of the substitution will be that. So for x to the 3rd power, we'll substitute u. For 3x squared dx, we'll substitute du. Okay? All right, now, all of this fits. I get this from that. Take the derivative of each side, 1 du, 3x squared dx. That's how we treat this. Okay? That's just the method. That's something you'll have to get used to. So let's do this. I'll rearrange this. And whether you rearrange it or not, that's up to you. I mean, everything's up to you. But right here in this step, that substitution fits, right? Right there, x to the 3rd power, I'll put u in place of that. 3x squared dx, I'll put du. Okay, if I do that, then this is how this looks. Cosine u du. That is as simple as it gets, right here. This substitution in that problem made it very simple. And here's what I mean by very simple. I've got a rule for it. Right there. Antiderivative of cosine x dx is sine x plus c. Okay, now that we're at this point, what's the antiderivative of cosine u du? It's sine u plus c. And to put our answer back in terms of the original variable we started with, I will substitute that u back as x to the 3rd power. So this is going to be sine of x to the 3rd power plus c. Okay, and then that's our answer. Now, can you see why that works, though? What's the derivative of this? What's the derivative of sine? Cosine. What's the derivative of sine of x to the 3rd power? Cosine x to the 3rd power, then times the derivative of x to the 3rd power, which is 3x squared. You check it, it works like all the others. Okay, let's do this one now. All right, so again, there's a somewhat complicated problem. All right, I'm telling you the way to reduce this is to substitute u as 1 plus t squared. Okay, see the 1 plus t squared? That'll be u. What about the du and the dt? What's the other side of this that we're supposed to work with? If we're going to substitute u as 1 plus t squared, then we have to substitute du is 2t dt, right? That's how these work. You choose the u, and as a consequence, you figure out what du should be, and you make the substitution fit. Now, for this one, I'm going to do a little bit of work, a little bit of algebra on it before I substitute, okay? Could you take this and write it this way? Say, sure, rules of algebra allow for that. This exponent of 4 here is an exponent of negative 4 there. Okay? And the 2t was above the bar and dt. Okay, it's all there. So right here, in this step, that substitution can be accommodated. 1 plus t squared, that will be u. 2t dt, that will be du. Okay? So, all right, let's see. U to the minus 4th power du. Everything can be substituted. This one is one you can work. What's the antiderivative of u to the minus 4 power? Well, that falls under this rule right here. X to the n power. N is some constant, except negative 1. So that would be done this way. U to the negative 4 plus 1 over negative 4 plus 1 plus c. Or let's do negative 1 over u to the 3rd power 3, right? So that's a negative 3. That's a negative 3. 3 down there. Exponent's positive plus c. Okay? So there, I got to this point. The rule takes me the rest of the way. My final answer will be negative 1 over 3. What's u again? Can I put that back in terms of the variable I started with? U is 1 plus d squared. Okay, so like this. Negative 1 over 3 times 1 plus t squared to the 3rd power plus c. All right. But do you see what the substitution's doing for us? What I want you to see at this point is that some decision is made about what u is going to be substituted for. As a result of that, we factor in du. We might rearrange our integral a little bit, but at some point, everything goes in, and then we can work it from there, all by the rules, okay? All right, so now we'll just practice that. It's like no matter how weird this looks to you, the first few times you see it, the method is practically the same every time, okay? So here's another problem, and me again telling you what u is, all right? Okay, so can you take it from here? If I tell you what u is, can you work that? Okay, so first you should think, well, if this is the substitution, if we're going to say u equals 1 minus 4x, then we also have to say that du is negative 4 dx, right? Derivative of u is 1 du, and derivative of 1 minus 4x is negative 4 dx. Okay, now let's see. Does that fit up here? Let me do this. U is right there, right? 1 minus 4x, that'll be u. Do you also see negative 4 dx to put the du? I mean, the objective is we have to substitute u and du. They both have to go in there. They both have to be substituted. I see u, 1 plus t squared. I see du, 2t dt. Here, though, I don't see that. There's u, 1 minus 4x. I don't see negative 4 dx, though. It's just not there. So, like, what do we do? Like, this doesn't go up there. So, this equation, or both of these, really, they're equations you can treat algebraically. Meaning, what do you do when you solve equations when you learn algebra? You can add the same number to both sides. You could subtract the same number from both sides. You can multiply both sides by the same number. You can divide both sides by the same number. If I take this and I multiply by negative 1/4, I will get this in a way that it works up there. Okay? I will get this in a way that I could substitute it. The way it is, I don't see negative 4 dx. It's not there. But this will rearrange it so that I can. So here's what I'll get. Negative du over 4 is equal to dx. Okay? Now, this and this have a place up there. And that's the goal. All right? Okay, so right there, if the substitutions here that I've circled are made, I will get u to the 1/2 power dx. Okay, so that's going to be negative du over 4. Okay, so yes, the substitution is made. The goal was to substitute the u and the du, and I've now done that. When we do substitution problems, that's how it works. Okay, all right. Now, well, what about this? This part's supposed to be easy. Once you make the substitution, you'll get something that you know how to do. What about that minus, and what about that 4? That amounts to a number in here. That says u to the 1/2 times negative 1/4 times du. Okay, so now that, I don't want anybody to miss that. So I'm going to go ahead and write it intentionally. Okay, this is 3 things. U to the 1/2 times negative 1/4 times du. Okay, all right. What about that negative 1/4? Do we have any options for that? Well, I've told you there are lots of rules, and that's the truth. There are lots of rules. There is this rule about factoring constants out of an indefinite interval. So yes, that's what we'll need to do. Okay, so we'll get negative 1/4 times u to the 1/2 du. Okay, we'll just factor out the constant of negative 1/4 carried along. All right, so let's see, negative 1/4. How do you work it from here? What is the antiderivative of u to the 1/2 power? Well, the form of that problem is u to the n, right? When we have our variable to a power, we add 1 and we add 1 like so. That's the rule that we want for this one. Okay, so that will be 3/2, and this will also be 3/2, and then we're done, so we put plus c. All right, final answer. Well, let's reduce the numbers. This is negative 1/4 times 2/3. Okay, that's what that looks like. When I divide by 3/2, that's the same as multiplying by 2/3. And so that will be, through some canceling, 1/6. Okay, so I get negative 1/6. And then what's u? Well, originally our substitution said u is the same thing as 1 minus 4x. So we'll get 1 minus 4x to the 3/2 power plus c. And there it is. Okay. All right. Now, so this one, I try to emphasize some of the same things in the others, that when u is given to be substituted something, we also have to account for the du. And all of these equations can be treated algebraically to make them fit up there if we need to. Okay, I can take this equation, I can divide both sides by negative 4 if it would suit my purpose. I can multiply both sides by negative 1/4. I can add a number, I can subtract a number, I can do whatever I need to. Now, through doing some examples, you'll see the way that works. Okay, all right, now in these, I gave you the u just so you can see how it works out once that part's known. Okay, now truth is, you will have to figure out what u is supposed to be. Okay, how do we know what the u should be? There's 3 answers. If you just practice doing problems, you'll find some patterns to it, and it will get easier. That's one answer. Okay, because generally that's something that you're going to have to figure out yourself. I gave it to you on the last problems, but only so you could see what happens once you get to that point. The next answer, we can choose u such that a multiple of its derivative is somewhere in the integrand. Or 3, we can choose u so that we get some basic formula that we're familiar with. Okay, and there are lots of formulas. All right, take this one. Why is the antiderivative of sine u du equal to negative? Well, because if you take the derivative of negative cosine u, you get sine u. That's why. All of these have the same rationale. If you take the derivative of the thing on the right, you get the thing on the left. Okay, so you could choose u with the goal of getting one of these. Okay, so there's all these formulas that we have to work with. I'm not going to go through them and talk about all of them right now, but they all have the same rationale for being correct. Okay, I'm going to keep this handy in case I need it, and I'll show it to you. All right, now let's look at some examples. Suppose that you're going to do this problem, and you need to know what to choose. You do this problem by u-substitution. And what I mean by that is you have to choose u to be something and then work it like the problems that I just showed you. You have to choose the u yourself figure out the du, and substitute it in the problem and work it. All right. So here's the thinking. Here's the rationale. Let's see. This will be like the second one. We choose u. Here's one strategy. This is one of several strategies. We choose u such that a multiple of its derivative appears somewhere else in the integrand. So here's the thinking that you might have on this one. If we choose u to be root x, what's the derivative of root x? It's 1 over 2 root x. Well, this is missing the 2, but that's okay. Remember, we can algebraically move things around if we're missing the 2. So the thinking might be, if I choose u to be this, then will this part right here be the du? Okay? Well, let's try it. I think it will. So I'm going to choose this. Here's the substitution that I'm going to choose to work with. I'm going to let u be root x. If I do choose that, I can choose anything I want to be u, but if I choose this to be u, that really will be the du. Du will be, let's see, what's the derivative of root x? It's 1 over 2 root x dx. Okay? Now, are these going to fit up there? I'll rearrange it a little bit. It might help you to see like that. Okay, so there's u. We got that. Can you fit the du? Let's see. Do you see 1 over 2 root x dx? No, I don't see 1 over 2 root x. I see 1 over root x, but that's okay. We can do something with the 2. We'll take this. We'll multiply both sides by 2. Remember, we can treat this like an algebraic equation. So if I do that, I'll get 2 times du is 1 over root x dx. That fits. There's u. There's the du. Okay? So, all right, here's what we're going to do. Between this and this, we will substitute successfully. All right, so here goes. This will be cosine root x. That'll be cosine u. Okay? And then 1 over root x dx. That will be 2 times du. So there you go. The substitution was successful. The goal with any substitution is to substitute u and du into the problem somehow. Okay? I had to rearrange a little bit. I had to move that 2 around, but that's okay. It worked out. Now that we're here, what about this? How do you work this problem? Well, that's one formula that we have access to. The derivative of sine is cosine, so the antiderivative of cosine is sine. What about the 2 there? Well, the 2 is just a constant, and constants can be factored out of indefinite integrals like this, okay? And then so my answer, so 2, what's the antiderivative of cosine u? That would be sine u, and then we're done with that, so we put plus c, we add the constant of integration. We'll put our answer back in terms of the original variable we had, which was x, so this will be 2 times sine of, what was u again? It was root x, sine root x plus c, okay? All right, so see, I chose that so that the du would also work. It was true. So remember the question I posed was, if I choose that to be u, will this other thing end up being the du? It turns out that it did. And that's the kind of thing that we want to happen when we do u substitution. Okay? All right. Now, so to do that, like you have to have some familiarity with calculus and you have to know your rules for derivatives. But I hope that you could look at this and say, yeah, if I did take the derivative of this, I would basically get that right there. Maybe with the exception of the 2. But, I'd get that, and then I could take care of the 2 later. All right? So that's the thinking. That's the second strategy, is just look at your problem, choose u to be something that a multiple of its derivative is somewhere else in the problem. Okay? Now let's look at another strategy. Remember, 3 strategies for doing this. How should you choose the u when you do this? By practice. Okay, well, practice you just have to do that second one. That's what I just showed you. The third one, choose u with the goal of obtaining one of these formulas, okay? Choose u with the goal of obtaining a formula that you know already. So, like with this one, when somebody sees this, they might say, well, this has to be something. If there's a way to work this, there has to be some kind of formula for doing it. So somebody might think like, see that power right there? Maybe that means that ultimately it will reduce to u to the third power, okay? Could this problem be reduced by substitution of u somehow, u to the third power du? Could it be like that? Does this, just the form and the shape and the way this looks, does it suggest that, okay? Well, so I claim it does. What substitution could possibly turn this into this? The only way this is going to become this is if you let that part be u, okay? So yes, when I pose this rhetorical question, could this problem end up being antiderivative u to the third power du, then the thinking is, well, then the only way that would have to happen is if you let that be u. So we'll choose this. The substitution that we're going to try is to choose u is 3x squared plus x. Okay? And if we choose that, what's the consequence of it? If that's u, what's du supposed to be? Well, the method would command that if u is 3x squared plus x, du is going to be 6x plus 1 dx. Okay? All right, now would that work? Does this substitution turn this into this? And it turns out that it does. There's u to the third power, and then 6x plus 1 times dx, that will be the du. Remember, the goal is to substitute u and du. They both have to go in, and here we have no problem doing that. Okay? So yes, this will be u to the third power, and then 6x plus 1 dx, that will be du. Right here in this step, that's what we get. Is that something that we can work? Was this substitution, did it turn that problem into something that's easy for us that we know how to do? Yeah, antiderivative u to the third power du is u to the fourth power over 4 plus c. Okay, and then since, after all, u is the same as 3x squared plus x, we'll get 3x squared plus x to the fourth power over 4 plus c. And that will be our answer. Okay? All right. Now, I mean, there's only so much detail that I can go into, right? I mean, we can talk about math all day if you want to. I could have checked every problem, and I actually think that when somebody's learning this, it's good to check every single problem. I think that the whole method will sink in better if you do that. So I've done this one. I told you my strategy. I thought that this here would become that, and I chose my u accordingly to make that happen, and it did, and it worked, and I got the answer. So the method's done. We've done that. But I would like to emphasize that there is a way every single time to know if you're right or not, okay? That all these can be checked. What would make this correct? What would make this correct just like every other problem before it? If I take the derivative of this, I should get that. That's what makes it correct. So one last thing I want to verify is that, well, is it true if I take the derivative of this? Did I get that? Does it really happen? Let me say like this. That 4 right there is a constant of 1/4 times 3x squared plus x to the fourth power plus c. Okay, so yeah, if I take the derivative of that, what do I get? Do I get this? Let's see. How do you take the derivative of this? Well, that constant of 1/4 gets carried. Then 3x squared plus x to the fourth power. The derivative of that is 4 times 3x squared plus x to the third power. Then times 6x plus 1. Okay, and then plus, okay, plus, carry the plus down. What's the derivative of that c? That constant of integration is just some unspecified constant, so that would be 0. And sure enough, the 4's cancel, and I'm left with 3x squared plus x to the third power times 6x plus 1. That is what I started with over there. Okay, so that checks it, that verifies it. That's how, no matter how I do a problem, that's how I know it's correct.